Okay, let me start. Today we're going to talk about the Gramschmidt process. Actually, this is lecture 11, so people starting. Let's recap what we have done so far. So in the lecture 10, we've talked about the orthogonal projections, right? So what was the orthogonal projection? The orthogonal projection means that okay, we have the subspace W here, and we have an arbitrary vector Y here. Then what we want to do is to find the Y hat, which is the unique vector in W space for Y minus Y hat is orthogonal to W, as you can see here, and Y hat is the closest to the Y here. So in this case, Y hat is called the orthogonal projection of the Y onto the W space, right? So why do we need this one? Actually, this kind of the properties of the Y hat provide the key element to finding the least square solution of the linear system, which will be discussed next week. So yeah, so I guess you remember this figure, right? So that's why we studied the orthogonal projections, right? So there was one more concept, orthogonal complement. So if a vector z is orthogonal to every vector in subspace W, something like this, right? Then z is said to be the orthogonal to W, right? So the other in other words, the set of the all vectors W z that are orthogonal to W is called the orthogonal complement. So orthogonal complement of W. So as you can see here, this z is the one of the orthogonal complement vectors of W, right? So this is also the complement, and then there was a very important theorem called the orthogonal decomposition theorem. In this theorem, we want to decompose the arbitrary vector y in Rn space to the into the y hat plus z. So where the y hat is in the W space and z is in the orthogonal complement space. So as you can see here, if we have the arbitrary subspace W and the arbitrary vector Y here, then what we want to do is to find out the orthogonal projection vector Y hat and the orthogonal complement of Y. So we can decompose the Y into the Y hat plus Z, right? So this is the main idea of the orthogonal decomposition theorem. So today we will use this kind of theorem to derive the Gramschmidt process, right? And then we can represent this Y hat, the orthogonal projection of Y onto the W space as something like this, right? With the Y orthogonal basis U1 through the UP with the Y, right? So this is the kind of the Y hat, and if we find out the Y hat, we can easily find out Z, because Z is equal to Y minus Y hat, right? So this is the orthogonal decomposition theorem, right? Right. So we proved this theorem here, right? Right. So here was the example. Okay, so because the U1 and U2 is the orthogonal basis for the W is equal to span of the U1 and U2, so we can write the Y as a sum of the vector in W and the vector of the orthogonal W. So in this case, the sum of the vectors, sum of the vector in W is just Y hat, and vector orthogonal to W is Z, right? So the problem is that we can decompose this arbitrary Y into the Y hat plus Z, right? So how can we do that? Because the Y hat is defined something like this, as you can see here, right? So by using the U1 and U2 and Y, we can easily find out the Y hat like this, right? And then if we find out the Y hat, we can easily derive the Z which is defined y minus y hat, right? So finally, that is something like this, right? So if you draw some figure for y here, y hat here, u1 here, u2 here, and z is here, right? So this is the orthogonal decomposition of the given arbitrary vector y and subspace w, right? So yeah, there was the geometry interpretation of the orthogonal projection, right? So if we have the subspace W with the basis U1 and U2, and if we have the given arbitrary vector Y here, that this equation is derived from the y hat 1 and y2 hat y hat 2, right? So y hat 1 is the orthogonal projection of the y onto the spanned by u1, so it can be something like this. So and y hat 2 is equal to y orthogonal projection of y onto the span by u2, so it's something like this, right? So finally y hat would be the y hat 1 plus y hat 2. So finally, so we can prove this orthogonal decomposition theorem in the 3D space, right? And what else? Yeah, and then there was another theorem called the best approximation theorem, right? So let's say the subspace W be the let W is the subspace of the Rn space, and let Y be the any vectors in Rn space. Then let Y hat be the orthogonal projection of the Y onto W, as you can see here, right? Here, right? Then Y hat is the closest point in W space to Y, right? So in this sense, that the length of the y minus y hat is smaller than the y minus v for whole possible v in W space. So it means that y hat is the closest point in W to the given vector y. Okay, so in this case, the vector y hat is called the best approximation to y by element of W, right? So in other words, okay, let me say there is a vector subspace W, and we have a y, and we want to find out the closest point in W space. So y hat will be the closest point. So in this case, y hat is called the best approximation to y. Okay, so this is the best approximation theorem, right? Which concept will be used in the least scale solution in the next week's lecture. And yeah, so there was some kind of properties, right? So yeah, also on the rejection. So yeah, so okay, let's go back to today's lecture. So today we are going to talk about the Gramschmidt process, right? So before starting, let's recap. So actually we just recap the previous lecture, but in here let's just recap the orthogonal projections and the complement again, okay? Because it is very important concept that will be in the following, right? So let's say we have a subspace W, arbitrary subspace W, and we have the vector Y on outside the W or inside W, in this case outside W, right? Then we want to decompose this vector Y into the Y hat plus W, where Y hat is the orthogonal projection of Y onto W, right? So in this case here, right? And with the Z, which is equal to Y minus Y hat. So Z is called the component of the Y orthogonal to W. Okay. component of y orthogonal to w. So this is the concept of the orthogonal projection and component. Okay. So today we will use this kind of concept to derive the Gramschmidt process. Okay. So yeah. Okay, let's start the Gramschmidt process. Why we need this one? The Gramschmidt process is a simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace. So by using the Gramschmidt process, we can produce or generate the orthogonal or orthonormal basis for any kind of non-zero subspace, right? So and then if we have the orthogonal So if we find out the orthogonal or orthonormal vector, orthonormal basis for any non-zero subspace of Rn space, then we can do many things such as finding least scale solution or eigenvalue decomposition or the singular value decomposition, which will be discussed in the remaining lectures in this course. So anyway, let's start the Gramschmidt process. Actually, this Gramschmidt process is related to the matrix factorization. So which matrix factorization we will discuss? There was the LU decomposition, right? Okay, let's use different color. LU decomposition, right? So by using the Gramschmidt process, we can also decompose the arbitrary vector A into the two separate separate matrix. So after finishing this lecture, please go back to the LU decomposition and please compare those kinds of the two matrix factorization technique, okay? So which will help you to understand what does it mean, okay? Okay, so before starting, let's start with the example. Okay, let W is the spanned by x1 and x2, where x1 is the 3, 6, 0 vector and x2 is the 1, 2, 2 vector. And the question is that construct orthogonal basis V1 and V2. Okay, so it was a problem. So first of all, x1 and x2 is the best basis, inherent basis. Why? Because basis of W. Why? Because the W is the spanned by x1 and x2, right? So it means that x1 and x2 are basis of W, right? But the question was, let's find out the orthogonal basis, not just basis, orthogonal basis V1 and V2. Okay, so before starting, what is the orthogonal basis? What is the orthogonal basis? Okay, so if you go back to our lecture now 9.2, there was the definition of the orthogonal basis, right? So an orthogonal basis for a subset W is the basis for W that is orthogonal set, right? So what does it mean? Also, what does the orthogonal set? There is the orthogonal set definition. So yeah, here, if a set of vector u1 through the up here, so set of the vector u1 through the up is said to be the orthogonal set if any pairs of distinct vectors from the set is orthogonal. As you can see here, ui inner product uj is equals to 0, right? So this is the definition of the orthogonal set. So the orthogonal basis means the set should be basis for W and it should be orthogonal set, right? So this is the definition of the orthogonal basis, right? So here V1 and V2 should be basis for W, and V1 and V2 should be orthogonal. So it means that V1 inner product V2 should be equal to 0, right? So let's find out the V1 and V2 that satisfy this constraint, okay? Okay, so let me start. So first of all, we can start from x1, okay? So as you can see here, there is the vector x1 and vector x2, right? What I want to do is to find out the orthogonal vectors from the x2 and x1, right? So how can we do that? First of all, we can start from the v1, which is equal to x1, right? And then v2 should be orthogonal to v1 or x1. Then how can we find out the v2? Because in this case v2 is the complement of the vector x2 orthogonal to x1. So if you go back to this definition, the vector z is called the component of the y orthogonal to w, right? So we have to find the v2, which is the component of the x2 orthogonal to x1 or the v1, right? So yeah, let's find that. So how can we do that? How can we do that? How can we find this v1? So if we go back to lecture 10, here, right? So if you find out the y hat orthogonal projection of the y onto the w, we can just find out the z as a y minus y hat, right? By using this one, right? So in today's lecture, let's use this orthogonal decomposition theorem. Okay, so first of all, we have to find out the P, which is the orthogonal projection of the x2 onto the x1 or v1. So then how can you do that? How can you do that? So if you remember this theorem, this one P should be vector x1 inner product vector x1 vector x2 vector x1 times vector x1, right? So because x1 and x2 is defined something like this, right? So x1 is 360. It should be 3제곱 6제곱 plus 0제곱 0 squared, right? And x2 and x1 3 times 1 plus 6 times 2 and 0 times 2. It would be 0 here, right? So 9 36 and 3 plus 12, right? So it will be 45 and 50, right? So yeah, in here we need this one. Yeah. So this is the 50 over 40, and the P should be x1 here, right? So x1 is equal to what? 360, right? So P is defined something like this, right? Then this V2 is equal to x2 minus P here, right? So finally it is defined something like this, right? Because the v2 is equal to x2 minus p is here, right? Here, okay? So x2 is something like this, and the p is something like this, right? Then finally, if you compute this one, the final v2 is equal to 0, 0, 2. Okay, so this is the definition of the v2. Okay, so now we have the v1 and v2 here. So and then v1 and v2 are orthogonal each other, right? Why? Because the v2 is the orthogonal v2 is a component of the x2 orthogonal to v1, right? So it means that v1 is and v2 is orthogonal each other, right? So because they are also basis, right? Because they are independent each other, linearly independent. So if you go back to their definition of the orthogonal basis, so yeah, where is that? Orthogonal basis. Here. So because they are orthogonal set, they are linearly independent, hence they are basis for the subspace spanned by W. So it means that V1 and V2 are orthogonal each other. So the set V1 and V2 are finally orthogonal basis for W. As you can see, lecture 9.22, right? Orthogonal set, so orthogonal basis, right? Okay, so we find out the V1 and V2. Actually, as you can see here, from the x1 and x2, we derive the orthogonal basis V1 and V2 using those kinds of the sequence, right? So actually, this is just the simple version of the Gramschmidt process. So from now on, we will derive the more complicating version of the Gramschmidt process, but the main idea of the derivation is similar to this example. Okay, so let's go to the more challenging scenario. Okay, so in this example, we have the vector x1, something like this, and vector x2, something like this, and it's not a vector x3, it might be vector x3, right? X3 is something like this, right? And then we already know the x1, x2, x3 is the clearly linearly independent. Thus, it is the basis for the subspace W, right? Because they are linearly independent. So this is the basis for the arbitrary subspace W, right? Then the question is to construct the orthogonal basis for W, right? So actually this is the goal of the Gramschmidt process. Okay, so let's find out the orthogonal basis for W in this case, right? Okay, here is a solution. So first of all, similar to the previous example, let's say V1 is equal to x1. Okay, it means that let's start V1 as x1 itself. So in this case, W space 1 is spanned by x1 and spanned by V1. So it means that, as you can see here, by defining the subspace W, subspace might be the line, right? If we just considering the one vector, right? So this is subspace W. So and then this is the orthogonal projection of the x2 to the subspace W, right? So that's why we introduced the subspace concept here. Okay, so in here we first introduce the subspace W1, which is equal to span of the x1 or span of the xv1, right? And then what we want to do next, we want to find out the v2, which is the orthogonal project, to the x1 or the w1, to find out something like this, right? Then how can we do that? The vector v2 will be the vector produced by subtracting from the x2 each projection onto the w1, subspace w1. Something like this, x2 minus p, right? So v2 is defined x2 minus projection, orthogonal projection of x2 onto w1 space, right? How can you do that? Because the y1 is spanned by x1 or v1, then we can compute this one, something like x2 minus x2 dot product x1 v1 over v1 inner product v1 and v1 as well. Or in this here it's not a v1, so okay, let me check. In here it should be v1, right? So yeah, here is the error. Yeah, v1, right? So yep. So what was the x2? X2 is here, and x2 v1 is x1, so x1 is here, right? So how can I compute this one? x2 is equal to 0, 0, 1, 1, 1. 0, 1, 1, 1. And v1 is 0, 0, 0, right? 1, 1, 1, right? So it will be just 1 plus 1 plus 1 plus 1, right? So in here 1 plus 1 plus 1 plus, and v1 is equal to 1, 1, 1, 1, right? Then 1 next, because it will be the 4 and 3. So finally here negative 3 over 4, 1 over 4, 1 over 4, 1 over 4, right? So finally v1 is equal to something like this, right? So as you can see here, we find out v1 and v2, right? We find out v1 and v2, and v1 is the component of the x2 orthogonal to x1. So let's draw the figure. Okay, so let's say there is v1, right? And there is a subspace w1 spanned by v1, and we find out v2, right? Which is the component of the x2, because x2 is here, was here, right? So in this case v2 is the orthogonal v2 is the component of the x2 orthogonal to x1 or orthogonal to w1, right? So in this case, the set v1 and v2 is an orthogonal basis for the subspace W. So this v1 and v2 will make a new subspace W2, whose basis is the orthogonal basis is the v1 and v2, right? So in this case, V1 and V1 and V2 are orthogonal basis for the subspace W. Okay. So now we find out the orthogonal basis W, V1 and V2, and then what next? We have to find out another vector V3, right? Orthogonal to V1 and V2, right? Because the V1 and V2 and V3 should be orthogonal each other, as you can see here. So our goal is find out V1 and V2 and V3. Okay. Okay. So let's do that. So okay, before move on, there's one more optional step. If appropriate, scale the V2 to simplify the later computation. So because in V2 here there is some kind of the flexion values, right? So by multiplying 4 on each how to say, each element, V2 should be -3, 1, 1, 1, like this. So rather than using the V1 itself, we can use the resized version of the V2 to make the later computation feasible or the efficient, right? So now we have the V1 and V2, right? Then let's find out the V3, right? So, and similarly to the V2, let V3 is the vector produced by subtracting from X3 each projection onto the subspace W2. So now we have the subspace W2 here, right? Let's draw the subspace W here. And let's say there is a vector x3 here, right? Then what we want to do is to find out the component of the x3 orthogonal to W2 space. This is W2. So W2 space. So okay, so it should be W2 is here, right? So to find out this W, we can subtract from the x3 to the each projection onto the subspace W. So it's really hard to draw, but there is a orthogonal projection of x3 onto W2, right? So this V2 is computed by subtracting x3 and its orthogonal projection of x3 to the W2, this point, right? This vector should be same to this one, right? So yeah, this is the way to find out the V3, right? So okay, so to compute this one, we first find out this point. So it will be something like this, right? So projection, orthogonal projection of the x3 onto the W2 space, right? Then how to find out this one? We can use the basis for the W2 space, or the orthogonal basis of the W2 subspace, right? So, and then let's go. Yeah, here is our lecture 10. So if we have the orthogonal basis, something like this, we can represent y hat like this, right? So because we have the V1 and V2 and x3, right? So we can compute x3 inner product V1 over V1 inner product V1 times V1 plus x3 inner product V1 over V2 inner product V2 times V2, right? So how can we do that? Because x3 is here, right? And V1 is just x1, so it should be here, right? So, and V2 is equal to something like this, right? So, the scaled version of the V2 is something like this, right? Then you can compute this one yourself, right? So please to derive this yourself, okay? In this lecture, we will just skip this one because we have another things to do here, right? So finally the output of this equation will be the 0, 2 over 3, 2 over 3, and 2 over 3, right? And then how can I find out V3? Because the V3 is the component of the X3 orthogonal to W2, right? So X3 is here, and the orthogonal projection of the X3 to W2 space is here. So it will be here, right? And what was the X3? X3 was the 0, 0, 1, 1. So 0, 0, 1, 1. And this one is the 0, 2 over 3, 2 over 3, 2 over 3, right? Finally, V3 is equal to this one minus this one, right? So it should be 0, negative 2 over 3, 1 over 3, and 1 over 3, right? So this is the V3, right? So if we draw this kind of thing on the space, actually I draw this one in here, but there is more fancy figure here. So anyway, here is the W2 space, right? And here is the X3, right? Then, okay, so W2 has the two orthogonal bases as V1 and V2. So the orthogonal projection of the X3 onto the W3 will be what? Here. So V1, X3, V1 plus V2, X3, and V2, like this, right? So this is the orthogonal projection of the X3 onto the W2 space. Then this V3 will be the component of the X3 orthogonal to the W space, right? So it will be X3 minus projection X3 onto W2 space, right? So finally, because we already know the X3 and projection of the X3 onto the W2 space, then we can derive the V3, right? Interestingly, here V1 and V3 is orthogonal each other, and V1 and V2 is orthogonal each other. V2, V3 is also orthogonal each other, right? So it means that V1, V2, V3 is the set of the orthogonal bases, orthogonal set, right? So V3 is in the W space because the X3 and projection of the X3 onto the W2 are both linear combination of the X1 and X2 and X3, right? Actually, X2 is the linear combination of this one, and this one is also linear combination of the X1, X2, and X3. Why? Here, as you can see here, right? So they span W. So because V3 is the X3 minus projection of the X3 onto the W2 space, so V3 is also in W space, right? So the question was to find the orthogonal basis for the W space. Now we proved V3 is also in W space, right? Thus, V1 and V2 and V3 is the orthogonal set of the non-zero vectors in W, right? Orthogonal set because they are orthogonal each other and V3 is in W space, right? Hence, this set is a linear combination, linearly independent set in W space. Why? Why? If you go back to our lecture 10, lecture 9.2. Yeah, here there was the theorem. So if the arbitrary set is an orthogonal set, then this set is linearly independent. Why? Because we proved this one, something like this, right? So in here, because this set is orthogonal set, so they this set is a linearly independent set in W space, right? And note that W is the three-dimensional space because it is spanned by linearly independent set x1, x2, and x3, right? Right? Then by the basis theorem in lecture section 2.9, so which was a lecture 7.2. 7.2, there was a basis theorem. So let space H be the p-dimensional space. What was the dimension? The number of the bases, right? Then any linearly independent set of the exact p element in H space is also automatically is the basis, right? Or also any set of the p element of H's that span H is automatically basis for the H space, right? So by using this theorem, this set is linearly independent, right? And W space is a three-dimensional space. Then finally, this set is an orthogonal basis. Orthogonal basis W. Okay. So this is what we want to find, right? So in other words, if the subspace W is spanned by x1 and x2 and x3, then we can find the orthogonal basis v1 and v2 and v3 by using the x1 and x2 and x3, using this kind of process, right? So by step 1 through the step 3, right? Okay, so actually this is the way to find out the orthogonal projection using the Gramschmidt process. Okay, actually you already know how to use the Gramschmidt process because it was just only Gramschmidt process, but in here we will derive the Gramschmidt process in a systematic way, okay, or formal way, okay. So here is the Gramschmidt process. Given a basis x1 through the xp for the non-zero subspace W of the Rn space, then we want to find out the orthogonal or orthonormal vectors of the orthogonal or orthonormal vectors for subspace W, right? By using this kind of the basis. Then how can we do that? So our goal is to find out the V1 and V2 and V2 and Vp. They are orthogonal set. Orthogonal basis. Right. Let's do that. First of all, similar to the previous examples, let's start with the x1, right? And then v1 will be the component of x2 orthogonal to span by v1. So if we subtract this, right? So I will not draw the figure in here because the figure was here, right? So please imagine this figure here. And then in this case v1 and v2 is orthogonal each other. And then we want to find out the v3. So v3 will be the component of x3 into the component of the x3 orthogonal to v1 orthogonal to w2 space spanned by v1 and v2. So in this case, the orthogonal projection of the x3 onto the v1 and v2 space something like this, represent something like this, right? So v3 will be something like this. So in this case, by using this one, v1, v3 is equal to 0, v2, v3 is equal to 0, right? So it means that v1 and v2 and v3 is orthogonal each other. Orthogonal each other, orthogonal set. So they are orthogonal each other, right? And then generally, if we want to find out the VP, then we can find out the component of XP orthogonal to the space spanned by V1 through the VP minus 1, right? So it will be compute this, something like this, right? So actually this is the Gramschmidt process. So by using this process, we can find out the V1, V2, V3 through the VP here. Then this V1 and V1 through the VP is done orthogonal basis for W, orthogonal basis W, right? Because they are bases and they are orthogonal each other, right? And then in addition, span of the V1 through the VK is equal to span x1 through the xk for k is larger than 1, lesser than smaller than p, right? So it means that, let's think about this space. So the spanned by v1 through the v3, spanned by v1 through the v3 is equal to spanned by x1 through the xp, spanned by x1 through the xp. Okay, so it means that span v1 through the vp is equal to span x1 through the xp. Okay, so by using this kind of the Gramschmidt process, we can find the orthogonal basis for the double space. Okay, so this is called the Gramschmidt process, right? So actually there is the fancy proof in our textbook for the Gramschmidt process, but in here we will just skip the proof because we can easily understand it from the previous examples, right? So we will just skip the proof, but please try to understand why this Gramschmidt process make the orthogonal basis by using this kind of the procedure, right? So this is the Gramschmidt process, right? And then we already know the orthonormal basis, right? In the previous example, we constructed the orthogonal basis V1 and V2, right? It was the first example, right? Then what was the orthonormal basis? What was the orthonormal? It should be length 1, right? Then how can we make it? By normalizing the original vector v1 as a length of the v1, right? So vector u1 should be something like this, and vector u2 should be something like this, right? This is concept of the orthonormal basis, right? Yeah, that's it. So today we introduced the Gramschmidt process to find out the orthogonal or orthonormal basis for the arbitrary subspace W, right? Then by using this kind of concept, we will introduce the QR factorization, which is one of the most popular matrix factorization technique, right? So let's see this one. Let's see the QR decomposition factorization by using the Gramschmidt process. Okay.